So something that we didn't really have time to look at during the actual course was dealing with differential equations. And turns out there are two times when you really encounter this. One is with drag force problems. We're going to look at those first. And the other is with simple harmonic motion. So I'll do a second video where we deal with that. So, drag force problems and differential equations. First of all, what is a differential equation? That's a good question. It turns out that a differential equation is an equation, pretty simple. It's an equation that has a derivative in it. And of course, I'll show you what that means momentarily, but basically, if an equation has a derivative in the equation, then it's called a differential equation. So, as I said, drag force problems. Let's get into that and see how differential equations appear. So, we did talk a little bit about drag force, that when something is moving through the air, it will experience a force in the opposite direction that it's moving. And if you get a question about drag force, they will usually give you a formula, a formula for the drag force. And typically it's something like F equals negative BV. Sometimes they'll say F equals negative KV. Really doesn't matter what they use for that constant there. More rarely, they might say F equals negative BV squared or F equals negative KV squared. It actually depends on how fast the object is moving through the air. At slower speeds, drag force is usually directly proportional to the speed. At faster speeds, is proportional to the speed squared. So really just whatever formula they give you, go with that formula. By the way, the negative sign, that sometimes messes people up. The only thing that the negative sign means is that the force is in the opposite direction of the velocity. If you think about it, if something is falling, so the velocity points that way, the drag force on it is going to be upward. So the force is going to point that way. The force and the velocity are going to be in opposite directions. So it doesn't automatically mean that the force is negative. It just means that the force and the velocity are in the opposite direction of one another. So let's start by thinking about what some graphs that involve drag force would look like. Let's talk about if you drop something, what its acceleration versus time graph looks like. You know, and let's just deal with magnitudes. Let's not worry about negative signs. So if you drop something and there's no air resistance, it's going to have a steady acceleration of negative 9.8. Well, if we're dealing with magnitudes, we'll just call it 9.8. But with drag force, the acceleration starts off at 9.8, but eventually it has no acceleration. It doesn't accelerate anymore. So basically the acceleration decays over time, and the graph looks like that. How about the velocity versus time graph? Well, there, if there's no drag force at all, if there's no air resistance, velocity just continually increases. And again, we're dealing with magnitudes here. But if there's a drag force, eventually you reach a top speed. It's called the terminal velocity. And so the graph ends up looking like this. Over time, it reaches an asymptote, and it plateaus there at this number here, which is the terminal velocity. Now, very typical, one of the questions will be to derive a formula for the terminal velocity. So you should know how to do that, and it's very easy. If you think about a free body diagram, a falling object has mg, the force of gravity, downward on it, and it's going to have the upward drag force. Let's call it bv in this situation. Terminal velocity occurs when these two forces are exactly equal to one another. Then the forces are balanced, and it no longer accelerates. It doesn't accelerate anymore. It falls with a constant velocity. And so to figure out the formula for terminal velocity, again, it's a common question, really easy to answer. That happens when BV is equal to mg. When those two forces are equal to each other, you are not accelerating anymore. You're at your terminal velocity. So that means that V is equal to mg over b. And that would be the answer to that question. That's all there is to it. Lots of times they want you to label your graph. Sometimes they'll ask you to sketch a graph. And so you'd want to label this asymptote, mg over b. So that's one question you'll get, an easy one to answer. Let's talk about a more difficult question. They might say something like this: write, but do not solve the differential equation that can be used to write a formula for velocity as a function of time. So this is interesting that it says write but do not solve. This turns out to be very easy if they ask you to do that. The place to start, always start with net force equals mass times acceleration. And let's see how that works. You should always be thinking about a free body diagram when you use net force equals mass times acceleration. There's our free body diagram. Now I will say that when you solve these problems, it is best, it works out the way, so to speak, they want it to, if you take the falling direction, the downward direction, to be the positive direction. You know, you can really say either direction is positive, but it does work best if you say the downward direction is positive. In that case, your net force is going to be mg positive minus bv. bv is in the opposite direction. That equals ma. And so then you're almost there. I said earlier, over here in the earlier paper, that a differential equation is an equation that has a derivative in it. And so let's take a look at what we have right here. This doesn't have a derivative in it, but it's really easy to put one in there. mg minus bv equals m, and acceleration is just the derivative of velocity with respect to time. That's it. You're done. If that's your question, if the question is simply to write but do not solve, that's all you have to do. Use net force equals ma and ultimately replace a with dv dt. And that's it. You're done. So if you get a question like that, be happy because it's pretty easy. Now, the hardest thing would be if they ask you to solve the differential equation for a formula for velocity as a function of time. That would be the hardest thing. And it really is, all it is integration. It just takes a little bit of time, and you need to know the tricks of the technique. So let's take this equation. Let's integrate it. Now, to integrate it, you want to separate the differential variables. You want to get dv on one side, dt on the other. That's fairly easy. dt times mg minus bv equals m dv. The other thing you want to do is you need to get like variables on the same side. So here's a v, here's a dv. They need to be on the same side. And they need to be connected by either multiplication or division. That's the only way to integrate, if the two variables are connected by multiplication or division. So I can't simply add bv over to this side. So I'm going to divide everything that's in the parentheses over to the other side. So I have mg minus bv on the other side. Now these two variables are connected by division, and that gives you a situation where you can integrate. In fact, that's our next step. Integrate this side, integrate this side. You should think about the limits of integration. We're going to start at time 0. We're going to end up at some arbitrary time. We're dropping it from rest, starting at a velocity of 0, ending up with some arbitrary velocity. This side, I'm sure you recognize, is super easy to integrate. In fact, if we do the integration, you just get t. Done. The other side, a little trickier. How do you integrate this? Well, maybe you recognize we're going to have to do u substitution. So let's let u be equal to mg minus bv. And that means that du, got to take the derivative of this. Mg is a constant. This is not. We're going to have negative b dv. If I take the derivative of that, it's negative b dv. So here I have u. I don't have negative b dv here, but I need it in order to do this, excuse me, substitution. So I'm going to have to do a couple things. Let me pull the m out from outside of the integration sign. So get that out of the way. And like I said, I need to have negative b dv up here. So let me just multiply this by negative b. And now you'll notice I have, if this is u, this is du. I'm in good shape. But I need to do something about the fact that I just multiplied by negative b here. So I need to multiply by negative b on the other side of the equation as well to keep it an equation. All right? So let's see what we got now. Now I'm going to substitute mg minus bv. That's u. And notice that du is negative b dv. I've got negative b dv right here, so I'm just going to substitute that with du. Sometimes people ask me, where'd the negative sign go? Well, it's part of what du is. Literally, I can replace this entire thing, including the negative sign, with du, because that's what du is equal to. All right, let's integrate this now. So I have negative bt, excuse me, equals m times the natural log of u. And now let's substitute back in what u is equal to. So the natural log of mg minus bv. Let's talk about our limits of integration, which are from 0 to v. All right, I'm going to continue this on another piece of paper. What I'm also going to do is I'm going to divide that m over to the other side just to get it out of the way. So negative b over mt is equal to, and let me put in the limits of integration. So ln mg minus bv, that's the one limit of integration, the top limit, minus ln of mg. When I put in 0 for v, for the other limit of integration, the bv disappears. Now this can be rewritten by the rules of natural logs as a division, mg minus bv over mg. You can write it that way. Now, to get rid of the natural log, we have to take e and raise e to the power of both sides. That's going to give us e to the negative b over mt on the left side, and it's going to give us mg minus bv over mg on the right side. And so let's remember what our goal is. Our goal is to write a formula for velocity. So at this point, I want to get v by itself. It's just algebra now. I want to get v by itself. So multiply both sides by mg. I want to get I want to get v by itself. So maybe I'll multiply everything by -1. And I always like to work with my variable on the left-hand side. So let me switch sides here. So bv would be equal to mg minus mg e to the negative b over mt. I could factor out an mg. So that's 1 minus e to the negative b over mt. And then finally divide both sides by b. mg over b. 1 minus e to the negative b over mt. And that actually is our final answer. That's a formula for velocity as a function of time. And what I want to point out is how well that works with the graph I made earlier, the velocity versus time graph. It looked like this, and it had an asymptote. And remember, we said that the asymptote was the terminal velocity, which, if you look back, was mg over b. Notice how that works with this equation right here. Here's our mg over b right there. And if you put in a really large number for time here, because that's what an asymptote is, you're reaching it after a very large amount of time. In fact, put in infinity. What if we put in infinity for time there? You have e to the negative infinity. That's basically 1 over e to the infinity. 1 over e to the infinity. Well, that's pretty much equal to 0. So you'd have 1 minus 0. In other words, you'd have mg over b. So this equation becomes the terminal velocity after a very long period of time. And this expression, 1 minus e to the negative something, is very typical of this shape right here. I call it exponential growth toward an asymptote. So, so that's our equation for velocity. What about the acceleration? Well, let me rewrite our velocity equation. V equals mg over b times 1 minus e to the negative b over mt. Keep in mind that acceleration is just dv dt. It's the derivative of velocity with respect to time. That's acceleration. So let's take the derivative of this equation up here. Maybe I'll rewrite it. Distribute that mg over b. mg over b minus mg over b e to the negative b over mt. Well, by the rules of taking a derivative, this is a constant. Derivative of a constant is 0. The negative mg over b is a constant part of that, so I'm just going to write that outside there. When you take the derivative of an e function, you still get e to the negative b over mt, but then you have to take the derivative of this part right here, which would b over m as a constant, so the derivative of this is simply negative b over m. These are being multiplied, not subtracted from one another. Now we can do some simplification. The negatives times a negative, they're both positive now. B cancels out B, M cancels out M. What are we left with? A equals G e to the negative B over mt. Let's compare that to the graph I showed you at the beginning, acceleration versus time graph. Remember we said it looks like this, but that initially it's equal to g, and then it drops to 0 after a very long period of time. Well, what if we put in a 0 right here for time? If we put in a 0 for time, you're going to have e to the negative 0, same thing as e to the 0. Well, anything to the 0 power is simply equal to 1. If this is equal to 1, then at time 0, acceleration is just equal to g. And after an infinite amount of time, this is going to be equal to 0. So it matches our graph perfectly. So those are the basics of a differential equation drag force type problem. And if you want to practice these, and I really recommend you practicing them, take a look at the website that I've linked to for studying. And here are some past AP exams that have drag force problems. In 2013, question number 2. In 2012, question number 3, sort of, I'll say kinda. It's not quite like this, but it's similar. 2008, question number 1. 2005, question number 1. You can see how common these things are. In 2000, question number 2. Those are all ones that you might want to practice. Good luck with that.